So everybody, what would the shift be here? Stretch of 2, right 3, up 1, reflection over the X. Way to remember that. This would be a left 1, down 3. This would be a right 3, up 5, and then a compression of a half. Okay, way to remember. So if we know how to shift one function, we know how to shift all functions. That is true. We're going to be using that today right here at the beginning of the lesson. That's why I reviewed that with you. So last time what we did was a little activity to get us to understand today's lesson a little bit easier and see where things are coming from. We're going to be graphing rational functions officially today. Last time we saw and explored how they work. So let's first look at the most basic rational function here. This parent function, f of x is equal to 1 over x. Now what I want us to do is just bring our eyes right down here. At this, I've graphed f of x is equal to 1 over x here. So if you plotted points in our calculator, we would see this happening. Now everybody, we have a vertical, in this equation 1 over x, we have a vertical asymptote at x equals 0. Can anyone remember from last time why that might be the case, based on the equation? You're on the right track, but I think you're thinking of the wrong type of asymptote. I'm talking vertical here. Yeah. When x is 0, it's undefined, meaning x cannot be 0. You're right, x cannot be 0. So that's where this vertical asymptote comes from. The rest of you are thinking of the, yeah, you're awesome. You're thinking of the next type of asymptote. So where is this horizontal asymptote coming from? You were just saying it, the degree, right? Okay. All right, so everyone's saying that this horizontal asymptote came from the degree, right? So remember, this is what's happening at the horizon, at the very ends of our graph here. Now let's actually make sense of this today. Let's try to make sense of this. Let's plug in a really large value for x, because it's where it's approaching clear out here at the end of our graph, end behavior. So let's plug in 1 over 100. Isn't that pretty much 0? What about 1 over 1,000? Isn't that even closer to 0? So it's just getting closer and closer to 0 the larger x is. Now let's plug in a negative x value. Isn't that almost 0 but just a little bit negative, but still almost 0, right everyone? And same thing here, right? Even closer to 0. So it makes sense. It's what's happening at the end behavior of our graph. Awesome. So do you guys see how it's more important at the ends of our graph, not really necessarily what's in here by this asymptote necessarily? Awesome. Just wanted to point that out. Yes?
So, will it eventually, like, do the thing where it breaks and goes over it, or will it just always stay?
So this is a really, really good question. In fact, guys, we can actually cross horizontal asymptotes. Even if we did, it would still hug it right here. This one won't end up ever crossing because it doesn't have an X intercept. Because if you remember, don't our X intercepts, our zeros come from the numerator? Yeah. So in this particular instance, it will never cross our horizontal asymptote since there's no zeros here. Does that make sense? But they actually can cross horizontal asymptotes. But even if it did cross it, it will just stay right there by it then. So, and we're doing rough sketches so that we're not like we're not worrying too much if it crosses or not. But you're right, on this one it wouldn't. Okay, so now can't we take, sorry, I want to go back to this. Can't we take and shift this function around? This is a parent function we just talked about, right there it is. So couldn't I take and shift it right 2 units? What do you think would happen with this asymptote if I shifted it right 2 units? Shift right 2 units. What if I shifted the function up 4 units? What do you think would happen to our horizontal asymptote? Shift it up 4, right everyone? So this would be our shift left and right comes from, just like with all our other functions. Left and right we go opposite because that's grouped in with x. This is our shift up and down, right? Sign stays the same. And then this stretch or compression won't really matter. It's just like it'll stretch up quicker or slower. Our acceleration will be larger, either stretched or compressed. It's either slower or larger, but it won't really change the look of the graph much. And if I put a negative in front, wouldn't that take our function, instead of being up here, it would flip it down here? Right? Reflection over the x-axis. Do you see here's our x-axis? I reflected it, so wouldn't this then flip up here? Everyone see how this is working? Okay, awesome. So we have this. I just was plotting some points here. I didn't graph it. Here's our asymptotes, where they come from. So our vertical asymptote, just to review, our vertical asymptote was our air asymptote. If we graph it, it will say air at 0 because we can't divide by 0. That's our vertical asymptote. It's called an air what makes the denominator 0. Then our behavioral asymptote was our horizontal asymptote because that helps us know what the end behavior of our graph is. So as we graph it, the lower we get, the closer to 0 we got, creating our horizontal asymptote at the end of our graph was approaching 0. And then right here, as we get larger and larger, it's approaching 0 as well. Okay, awesome. So now let's shift this around here. So look at this function. In words, what would the shift be? Right 2. So we just said our asymptote used to be at 0, it's now at 2. There it is. And then it's up 3. So now we would shift our asymptote up 3 units. Now everybody think about why this would make sense. This is still our air, this is our air asymptote, right? X cannot be 2. So that's why it's at 2, right? Then everyone, I want to point something out. Let's just look at this portion of the graph here. 1 over x minus 2. Isn't the degree on top smaller than the degree on bottom? Yes. Which gave us a horizontal asymptote of 0. But then add 3 to that. 0 plus 3 is? 3. So that's why it's at 3. Right, everybody? But we just are looking at it like a shift. Okay, awesome. So now I could just plot some x, y points, everyone. But what do we know is happening? As at the ends of our graph, isn't it going to approach this? Isn't that the definition of an end behavior of our graph? Yes, it's going to approach a horizontal asymptote. And then we know it's going to come up and it's going to hug this, right? Because it can't cross it, so it has nowhere to go but hug it. So we know, and we can plot points. Look, I have some x, y points. I can plug in x, y points. So look, right here, over 1 up 2 is a point. Over 1 up 2. So we know it's in this section of the graph because we know it's going to come up and hug that asymptote, come down and hug that asymptote. Now once again, couldn't it cross? It's not going to in this type, but it can cross horizontals, right? It doesn't matter because it will just still hug it. Okay, awesome. Now looking at this, like if I plug in 3, I get out 4. So we're doing rough sketches today. You'd say, okay, well I know how this works. It's going to come up by the asymptote, and then it's going to come down by this asymptote. Rough sketches is all we need. All good? Easy stuff. Okay, let's look at another one. Let's go way quick through this one. So everybody, in this one, you would say this is a shift of right 3. So there's my asymptote, ding 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 at right 3. And then it would be up 5. So then there's my horizontal asymptote at 5, and then I could plot points. Everybody good? Okay, let's look at this one. Okay, so tell me, what is my vertical asymptote? X equals what? 4. So the first thing you do is take your highlighter, go to 4, and you would graph it with your highlighter, your asymptote. Then you would say, okay, my horizontal asymptote is at 6. So then on your graph, you'll highlight there as well. Then from there, you could plot x, y points. But we know that this is the parent function one, right? It's been shifted. Was it reflected at all? No, so wasn't it up here? Our parent function, that didn't change, right? Because this is just a shift from the parent function. Want to just hug the asymptote. That's not super accurate, but if I wanted to be more accurate, I could literally plot some x, y points. Does everybody understand? Awesome. Okay, I won't graph this one, but I want to point something out here. We have a negative on top here. That will not affect this, will it? Where would our vertical asymptote be? X equals negative 5. So then I would graph that, and then my horizontal asymptote would be at negative 6. Now, instead of being in this portion of the graph, wouldn't it reflect? So then you would just reflect them. Now it's up here and down here. But you could plot x, y points, couldn't you? Just plug in x, y points to see where it's at. Yes? Okay, awesome. What I want you to do is go to the homework and work on problems 13 and 14, then flip it over and do 21 and 22. But you guys have got to be way quick on the easier ones like this. We took way too long for hour doing these. Let's say one more thing. Let's look at domain and range on this one. Okay, domain is left and right, correct? Isn't this the one x value we can't be? True? So our domain, aren't we coming in hot from negative infinity? And then it's like, oh no, I can't be that value. I can't be 2. So it's coming in from negative infinity up to 2, but it doesn't include 2. True? All right, and then union, then after that, then doesn't it start again? Really close to 2. So then from 2, and then it goes to infinity for x, not including 2. You guys see how this will take care of all the values except for 2. Now our range, let's write out our range. Range is y values. So we're coming up, up, up. So we're coming in from negative infinity up to 3. Then we're jumping over that. So that's why I put a parenthesis, because that means not including 3, union. And then we go from 3 up to infinity. So hopefully that makes sense for domain and range. Continue. Here, I wanted you to start factoring, but we're going to move on. And then you'll be able to go to your worksheet and work. Okay, so here's the thing, guys. We just graphed the most basic shift from the most basic parent function, f of x equal to 1 over x. Now, we know that not all functions are a shift from the parent function. So not all rational functions are a shift from the parent function, but they do still have the same similar key features of the graph. They're still going to have vertical asymptotes, horizontal asymptotes, poles, and whatnot, which we saw last time. We saw lots of examples of different types of things. So the first thing I want you to write down in your notes is the word discontinuities. We're first going to talk about just discontinuities, this key feature of the graph. Discontinuities are what make the denominator 0. Now, discontinuities are going to create holes or gaps in our graph, like holes or breaks. So that's going to be holes or vertical asymptotes. So if I say to you, what are the discontinuities, I'm literally asking you, what are the holes and what are the vertical asymptotes? So that's what makes the denominator 0. That's where discontinuities come from. It's what makes the graph discontinuous from left to right. So I want to show you a few different graphs here. These are examples, 3 different examples of rational functions that are not a shift from the parent function. So there's more than one x, we know it's not a shift from the parent function if it doesn't have this form with the shifts. So everybody, at this first example here, we have x squared divided by x squared plus 1. What I want to point out is from left to right here. From left to right, I'm continuous. Look, I never have to pick up my pencil. It's connected all the way through. My domain here is all real numbers. Now, why is that? So our discontinuities come from the denominator being 0. So yes. Oh yeah, so let's explore that. So you'd say discontinuities come from when the denominator equals 0. So we'd say x squared plus 1 can't factor. True? Yeah. So we'd say, well, x squared plus 1 cannot equal 0. That is a true statement. So subtract 1. So you'd say x squared cannot be negative 1. Square root it. So isn't x can equal plus or minus I? Well, remember, if you can remember back to even when we were doing just simplifying, isn't it true that if there's a restriction with I, this is a real number line. Real numbers are the restrictions. So here this one has no restrictions in the denominator, making it continuous. Now let's look right here. This one is not continuous. Let me scroll up so the people in the back can see better. We have a hole, so that makes it discontinuous. So now let's look. I have this line here. I'm graphing from left to right. I have to jump over that value and continue onward. Why am I jumping over x equals negative 2? Why am I jumping over that value? It's a restriction. It can't equal. Now, what's making it a hole? Good. It's top and bottom, and we saw last time that when that happens, it's a hole, right? When they simplify out, they end up being a hole. So we're actually just graphing the function y is equal to x plus 3, but we know we restrict before we divide. Therefore, it creates a hole at that value. So we write holes, though, guys, as xy points. It was at negative 2, comma 1, wasn't it? So we write holes as negative 2, 1 was our hole. Everybody good? Okay, let's look at this discontinuity here. So as it's graphing, it's from left to right, all is good, all is good, all is good, and then it's like, uh-oh, I cannot be 2. So it's like wrapping down and it's going down forever. It's never crossing. Then after that, it starts again, really close at 2, but then continues left and right. There's a gap or a vertical asymptote in this graph at 2. Why is that? X equals 2, there is a gap. Because it's a restriction that didn't divide out, right? Creating a vertical asymptote, if you remember. So hole, divide out, vertical asymptotes do not, right? So those are our discontinuities. Awesome. Now, to know those things, to know if they divide out, you've got to have everything factored. So this is not on your worksheet, but let's go through and just look at these 3 things. So we're really good at this part before we move on to the horizontal asymptotes. Discontinuities are what make the denominator 0. So what would my discontinuity be here? Yep, x cannot equal 3. Okay, everybody good at that. What's my discontinuity here? X cannot equal 3 or, oh, that was actually, we're changing that problem. We're making the bottom and actually an x minus 1. So my other discontinuity is 1. Okay, got good. What's my discontinuity here? X cannot equal 0 or 2. Now we're going to tell our, whatever, we're going to tell this if it's a vertical asymptote or hole. Is this discontinuity a hole or vertical asymptote? Vertical asymptote. Yep, since it didn't divide out. So you'd say x equals 3 is a vertical asymptote. There are no holes. Moving on. With this one, x equals 3 is a vertical asymptote. Do you agree? Yeah. It didn't divide out. What's the hole? X equals 1. Now watch. everyone, you have to write holes as XY points. So watch what happens. We'd say, okay, our hole's like going to be at 1 comma some Y value. We don't know what that Y value is. Well, don't we see that these divide out? So we're actually looking at the function x plus 2 over x minus 3. We just have a hole at 1. How do I find a Y value if I have an X value in a function? Plug it right in. 1 plus 2 is 3. So on top we have a 3, and on bottom, 1 minus 3 is negative 2. So if we were going to graph the hole, it'd be over 1 and then down 1 and a little bit. Does everybody see? Awesome. All right. Our vertical asymptote here is at x equals what? 0 and x equals 2, because neither of those divided out. There can be many, many vertical asymptotes. We draw both of those in. What's my hole at? No hole. Does everybody understand how discontinuities work? They come from the denominator. Now notice in my example, everything was factored. You need it factored to know what will divide out. So you got to go through to your worksheet right now, factor, and then go through and answer your discontinuities. Only answering discontinuities right now, which are vertical asymptotes and holes. Those are discontinuities. Answer those right now before we move on to horizontal. Ready, go. Continuities. So let's move on. Okay, let's talk about and remember the rules for behavioral asymptotes, meaning what's happening at the end behavior or on the horizon when it comes to our graph. So, if you can remember, looking at this, for example, we have 2x squared plus 3 divided by x squared minus 1. Isn't the degree on top and bottom the same? Yeah, it is, right? The leading term, the degree on top is 2, the bottom one's 2. So what happens on the horizon if our degrees were the same? What's our horizontal asymptote? At y equals? Good thought, though. Y equals 2. True. It's 2. Where did he get 2 from? 2 over 1, right? Now y, let's think about why that would be on the horizon, at the very end of the graph. Yes?
Because you can factor out 2. I mean, it would give you a fraction, but you can't factor out 2, and you plug in.
You were on, going there on the right track. Anyone help him out? Why would it just be 2? Why can we just... That's kind of what you was going for. Anyone else? Not wrong, necessarily. No. Thinking of something else.
In the denominator.
This is me giving you a hint here. Aren't end behaviors at the ends?
Yes.
The far ends of the graph. Well, if I plug in 1,000, everyone look. 2 times 1,000 squared plus 3. 2 times 1,000 squared. If we have 1,000 squared, that's going to be some huge, huge number, correct? Yeah. The plus 3 is going to be so minuscule it doesn't matter, right? Barely anything. Then we have 1,000 squared minus 1. That's going to be some huge, huge number. The minus 1's not even going to matter. It's so little. Well, don't 1,000 squareds divide out then?
Yeah.
Leaving me with 2 over 1, guys, right?
Yeah.
Something divided by itself. Now it's not 2, because isn't this a little bit more than 2? And then isn't this a little bit less? So it's just close to 2. It helps us get our horizontal approaching. Does everybody see why it makes sense?
Yeah.
They divide out. It's going to approach that value, okay? So our horizontal asymptote, if the degree is the same, is the leading coefficient. So we would go and draw in our horizontal asymptote at 2. Are we good with that?
Yeah.
That's your first rule if you need to write it down. Horizontal asymptote, if the degree is the same on top and bottom, notice that you'd want it in standard form to look at that, are going to be the leading coefficients, which we saw last time. Okay, now what if, everybody, if we have x minus 3 over x squared plus 1, isn't the degree on top smaller than the degree on bottom? Can anyone remember y equals what is our horizontal asymptote? It's 0. Okay, now let's try to make sense of why this will always be 0. Let's think about this. Okay, so I've gone and plugged in 1,000 again, just to see at the very end of our graph, where would it approach? So let's think about this, guys. 1,000 minus 3. Once again, the minus 3 is not going to really matter much, right, when we're that big. Then on bottom, I have 1,000 squared. Isn't 1,000 squared way, 1,000 times 1,000, way, way, way larger than 1,000?
Yes.
So if you take something small, like a 1, and divide it by something huge, like 1,000, you take one piece of bread and divide it into 1,000 pieces, is there going to be any bread left?
No.
No, it's pretty much 0, correct? Not 0, there's a teeny tiny little crumb, but it's pretty much 0, right, everybody? You guys see how that works? The further out I go, the more I divide up that piece of bread, the smaller it gets, the closer and closer it gets to 0. So no matter what, if the degree on top is smaller than the degree on bottom, we'll have a horizontal asymptote of 0. There's your second rule. Hopefully that makes sense of why. Now I need to point something out, guys. Horizontal asymptotes can be crossed, because it's just where it's approaching at the end. It doesn't matter, really, it's not telling us what's happening necessarily right in here. It's more at the ends of the graph. What would my x-intercept be here? 3. So it would cross the horizontal asymptote, which happens, it's okay. Even if it crossed, let's say it comes in, it's still going to hug it though. It's still at the horizon. Does that make sense, everyone? Vertical asymptotes can't be crossed. It definitely can't be 0, right? Horizontal asymptotes only gives us where it approaches on the ends of the graph, which those aren't restrictions. Does that kind of make sense? Okay, so just remember, horizontal asymptotes can be crossed. It just tells us where it's approaching at the ends of our graph, which is really what's important. Now this is where it's different. Write this down. So we did see last time, if our degree on top, like x squared minus 5x, divided by x plus 1, if our degree on top was larger than the degree on bottom, we saw that there was no horizontal approach. It didn't approach our horizon. That was no horizontal asymptote, which was true. Now we didn't get into it because we just were exploring asymptotes, but what it actually creates is it's still going to approach something at the end. It's going to approach what's called an oblique asymptote. So if if the top degree is larger than the bottom degree, you're right, there's no horizontal asymptote. Instead, there's what's called an oblique asymptote. An oblique asymptote is, we're going to see them as slanted asymptotes. So not horizontal, but slanted asymptotes, interestingly enough. So where does that slanted line come from? Well, remember last time, if you'll recall, I told you we have to remember long division. And that's because we can take and actually divide and figure out what our line is. So let's look at this one. Let's remember long division. Now I had somebody point out, well, couldn't we use synthetic division for this one? Yes, but there are going to be a lot where you can't, so we're just practicing long division. So here we go. X plus 1 goes on the outside of our graph. On the outside of our house. On the inside is x squared minus 5x. Correct, everyone? So remember, we go off to the side, make a bulletin point. We have x squared, divide your leading terms. X squared divided by x is x, right? I told you we weren't going to spend a lot of time going over this. So x multiplies back down, we get x squared plus x. Do you agree? Yeah. Subtract 1, subtract, change the sign in other words. Add straight down, we get negative 6x, don't we?
Yeah.
So we have negative 6x divided by x, which is negative 6. So we have minus 6, we multiply it back down. So then we have negative 6x, and then it looks like minus 6. We change the sign. We add straight down, and we get a remainder of 6. So our equation, I'm going to write it up here, is y is equal to, we have our x minus 6, and then we have our remainder of 6. So plus 6 when we divide it by x plus 1. So what I'm going to do now, guys, is look, that is our asymptote. It's oblique. It's a line. Oblique means like, well, ours are going to be linear. So everybody, how do I graph this? Our y-intercept's at negative 6, right? My slope's 1, so up 1 over 1, up 1 over 1. There's going to be my oblique asymptote. Right there. So at the ends of our graph, it's going to approach that value, which isn't on the horizon. It's oblique. So, is anyone wondering right now, Ms. Christensen, what about that?
Yes.
Yeah? Okay, well, let's just explore why that might not really matter so much to us when graphing an oblique asymptote. So we know that this is our end behavior. If we plug in a really big value, right, where it's going to approach. If I plug in 1,000, what's going to happen here? It's pretty much 0, isn't it? Yeah. Isn't this is asymptote 0? So that doesn't really matter. So if this is 0 pretty much, as we get larger and larger, then all that matters is x minus 6. It's going to be such a little amount, it's not going to change your line. Does that make sense? It's going to be so minuscule that it won't even matter. So with this, that does not matter because it became 0 as we get larger and larger. It pretty much becomes 0. Does that make sense? So we only have to worry about this part. There would be your oblique asymptote. So what were the 3 rules we just did? If the degree is the same, right? If the degree is the same, what was the rule? The horizontal asymptote is at the leading coefficients. If the degree on top is smaller than the degree on bottom, it's a horizontal asymptote at 0. And then if the degree on top is larger than the degree on bottom, there's an oblique asymptote. Okay, so let's go quickly. These are on your worksheet. Here we go. Let's answer some off the worksheet. What is the behavioral asymptote? Meaning, where's that heading at the ends of our graph? Is it a horizontal asymptote or oblique asymptote? Let's look. Degree is the same. So what is it? Y is equal to what? 3 is our horizontal asymptote because the degrees are the same. Boom, 3. Right, everybody? Questions? The degrees are the same. We talked about why they would just divide out. And the minus sign x won't really matter much, and the minus x won't matter much. Okay, number 2. Look at your degrees. Behavioral asymptotes come from the degree. What are the degrees? Both 1. So what is our horizontal asymptote at? 1/3, right? 1/3, the leading coefficient. So that's a horizontal asymptote at 1/3. All right, let's do this one. Notice the degree on top is smaller than the degree on bottom. Our horizontal asymptote will be at y equals 0. Now think about why that makes sense. If I plug in 1,000 divided by 1,000 squared, it's going to be so small because 1,000 squared is so much larger on bottom. It's cutting it up so small it's pretty much 0. Okay, let's look at number 4. What kind of asymptote do we have here? 2 is on top, 1 is on bottom. Isn't that higher on top than bottom? Yes. So it would divide out to become an x, right? We got to go through it though. So we'd say, okay, so it's an oblique asymptote. It's a slanted asymptote. So let's go through and do synthetic division or long division. Let's do long division just to practice. So x minus 4, house. So here we go. Adding straight down. Now will the rest matter? No, because the remainder doesn't matter for this. So you'd say I have an oblique. Asymptote at y is equal to x plus 2. You guys understand how to do behavioral asymptote? Look at the degree. Awesome, but try, you guys got to know this stuff for calculus next year. Understanding it's what's going to help you remember it. But try to as you go through and find these behavioral asymptotes, why they are what they are. Okay, ready, go. I want you to go back to 1 through 12 and answer the behavioral asymptotes. Now understand, with a behavioral asymptote, you will want to find those if it's in standard form. So you can compare the degrees appropriately. So go back to standard form for behavioral asymptote. You know what I mean by standard form, not factor form. Okay. So focusing. So it says graph. These are the steps you go through. All it's going to say is graph. You're going to go through and find in the same order as the front. Discontinuities if they're vertical asymptotes or holes. That's our first step. So everybody, we have discontinuities. I'll just write D for discontinuities. X cannot equal -3. Now honestly we should probably have factored first. So -1, x plus 2, and then on bottom our x plus 3. We should factor first. Okay, awesome. Now vertical asymptote is that x equals -3. Any holes? No. Okay, let's graph that. So you would take your highlighter and you would go to -3, and I want you to highlight your asymptote. Okay. Then moving on, you'd say, now what's my horizontal asymptote? You want to look at it in standard form. So back to here. The degree on top is 1, and on bottom it's 1. So it's the same. So it's our leading coefficient, right? Y equals -1 is our horizontal asymptote. That's what we just went over. Okay, so I'm going to go to -1 and draw in my horizontal asymptote. Okay. Now we're going to graph. Now we have to graph it. So these are the points. We're just going to plot points. But I do need you to plot specific x, y points, everybody. So notice it says do the x and y intercepts. That is important. And then plot more points if you need to. So let's find the x intercept. The x intercept, isn't that the numerator when we solve it? If you remember back to last time, the zeros, right? What would my x intercept be? -2, guys. Set it equal to 0 and solve. It's at -2, 0, right? So I'm going to go to -2, 0, boom. Now look, we have to fill in for all x's here. So as we plot over here, don't we know for a fact that it's going to come up and approach this asymptote? Yeah, because it can't cross it. And then won't it come down and hug this asymptote? Well, what if you didn't know? Start plugging in some more values. And I did this last time too. My Y-intercept is a value I should find. So Y-intercepts are when x equals 0. So if I plug in 0, I'll have -2/3. So over 0, -2/3. Boom. So there's 2 points. We know what's happening here. Now, there's going to be a graph on this side of the vertical asymptote somewhere, either up here or down here. We don't know. Let's plug in a value, maybe -4. Sure. So now pick some more points. We found the x and y intercepts. After that, just plot some more points. So if I plug in -4, what decimal do I get? No, what don't you get? -2. So we're going over -4 and then down 2 units right there. Boom. Well, then we know it's going to come by this asymptote, by the definition of a vertical asymptote. It never crosses a vertical asymptote. And then isn't it coming up and approaching this asymptote on the horizon? Done. Not too bad, right? Okay, let's do some that are going to get a little bit more dense, like this one. Okay, here we go. So we would say, okay, before we do this, we should probably factor it. So on top we have a 4x. Then on bottom we factor out an x, and then left is x squared minus 4. Well, that factors more. So we're actually dealing with this. 4x, and then on bottom are we dealing with x, and then how does that factor? Okay, awesome. So now let's write out our discontinuities. Our x cannot be 0, -2, and 2. Now, vertical asymptotes are wholes. Let's see what they are. Vertical asymptotes are at x equals 2 and -2. So that would be the first thing. I'd go over and take my highlighter, and at 2 I'd draw a vertical asymptote, and at -2. We know it will never ever cross that, but it's going to approach that. And then our whole is at 0, comma, let's figure it out. So we would remove it. So our function we're actually looking at is this. 4 over x plus 2, x minus 2, right? Or the same thing as 4 over x squared minus 4. Okay, either of those is what we're looking at now, right? Okay, let's plug in 0. 4 divided by 0 squared minus 4, isn't that -1? So that is just a point on our graph, guys. An xy point. We have a hole, but it is an xy point at 0, -1. So I'm going to go over 0, -1 and create a hole. But that is a point on our graph. Because remember, it connects, right? It's just a graph, but it just jumps over that value, if you can recall. Okay, so now let's plot some x and y. Oh, no, we need our horizontal asymptotes. So let's squeeze that in here. What's my horizontal asymptote? 0. The degree on top is smaller than the degree on bottom. Y equals 0. So now I'd go here and draw in y equals 0. Now remember, it can cross horizontal asymptotes, possibly. So do we have any x intercepts? No. So this one, it won't cross it. It can, but it won't. Okay. So no x intercepts. Let's find a y-intercept. Well, let's look at the graph here. My y-intercept's actually already been found, isn't it?
Well, yeah, there is.
Yeah, there isn't one technically. It's a hole. Okay, awesome. So now let's plot some more points. We need to connect all of our x's somehow. So let's plug in maybe a 3. So everybody go. Plug in 3 right there. Then somebody else. Plug in a 1. I'm all out of order. 3 is what?
4/5.
Okay. Yeah, let's just do decimals. That's easier to graph. It's easier for us to visualize. You're right. 3 over 0.8. So I'm going to go over 3 up 0.8. Well, now don't we know what's happening?
Yeah.
We're in this region. Won't it come up by this asymptote? Can't cross it. We already know it won't cross this one. Didn't we just find there's no x-intercepts? So boom. We're done with that half. Now look, we need to plot some points between this hole and this asymptote right here. And then we need to plot some points between this hole and this asymptote. Because maybe, look, let me show you what it could do. So, well, with this one it can't cross. But there are times when it could come up and cross and follow the asymptote because it can cross the horizon. This only really helps us with this end behavior. But it couldn't cross the vertical asymptote, or it could come down like this. Do you guys see what I'm saying? Okay, so let's plug in a 1. What do we get? -1.3. So we're over 1, -1.3. That's down there. So we know it's going to come and hug that asymptote. Awesome. Now let's plug in maybe -1. So if we plug in -1, we get -1.3. So then we're over -1, -1.3. So it must be coming down and hugging that asymptote, never crossing a vertical. Now we need to plug in something on this side of the x axis of that vertical asymptote, which maybe plug in, I don't know, a -3. Yep, 4/5. So -3, it's up 4/5. So then it must be like this. And we're done. There were just kind of 3 sections, right? We just got to make sure we check all the sections and fill it in appropriately. You can always plot as many points as you want. Okay, let's do another one. I'm going to go to this one. Okay, let's do this one. Here we go. Factor the top, factor the bottom. What multiplies to be -8 and adds up to be -2? 4 times 2? Yeah. -4. The top factors to be x minus 4 and x plus 2, right? Then on bottom we factor out an x, left is x plus 3. Awesome. Now we would say, so our vertical asymptotes are at x equals 0 and x equals -3. Good. So I would draw that in. At 0 and at -3. Awesome. Then we would say no holes. So moving on, holes none. Let's do horizontal asymptote. Look back. I like to look back at this standard form. Degree's the same, so wouldn't it be at y equals 1? Okay, y equals 1. So now I'm going to go up and graph that 1. Then from there we plot x, y points. Remember, I specifically want you to graph X intercepts, Y-Intercepts, and then plot any other points you want. Now let's look at this one. There could be X intercepts. Isn't it the numerator? So our X intercepts are at 4, 0, and -2, 0. So let's go plot those points. -2, 0, it's crossing the x-axis there, and over 4 of 0. Boom, there. Now our y-intercept, look at our graph. It will never, ever cross a vertical, right? So there's no y-intercept. So then plot more points. Well, let's think about it, guys. This, isn't it going to come and hug this asymptote? Yeah, but what if I didn't know for sure what to do? I could plot 1 and figure out the point, right, everyone? But I'm doing rough sketches. I know it's going to come and hug this asymptote. It's going to come up and hug this asymptote. But you can plot as many points as you want. Now, I am going to plot some points in here just to make sure, because it can cross horizontal, can't it? So it might go up, or it might go down. Let's see. So I need someone to plug in a -1 for me. Okay, so that's decimal 2.5 halves. Okay, whatever. 5 halves. Okay, then I need someone to plug in. We don't know, but look, between this 0 and here, we don't know if it goes up, right? Or it goes down. So I need someone to plug in -2.5. Not to, like, see, a lot of you are just sitting there waiting for everyone else to do it, and that's why it takes so long. Because it's the same people every time. So we already know it's -1 up here somewhere. So we know this one is actually coming up and following that asymptote. -2.5, what do we get? If you're not doing that, then you need to be plugging in -4. -2.6. So we're going over -2.5 and then down 2.6 roughly. So we know it's coming down. Does everybody see though how it helps me know if it's going up or down? Okay, awesome. And then plugging in -4. Okay, so we know it's up here. -4 up 4. So we know it's up here, so then it must go like this. We're just doing kind of rough sketches. Are we all okay? Feeling pretty good? Pretty easy? Do you feel like at this point you want more examples, or are you ready to dig in on your own? More examples or dig in on your own? Okay? Yeah? Leave an example up and let you dig in. Really the best practice is digging in and exploring. And then asking questions. Okay, awesome. Ready, go! Okay, yeah. I think you do want to see one with an oblique. I really do. Okay, so with this one, you would say, so if we try to factor the top, it doesn't factor. If it doesn't factor, nothing divides up, correct, everyone? So if that's true, then our vertical asymptote, since this doesn't divide out with anything on top, is x equals 2. So we'll go way quick though. At 2. Then when we look at our horizontal asymptote, notice the top is larger than the bottom, giving me a oblique asymptote. So I'm going to use long division, I guess. So x minus 2 Then we have 2x squared minus 3x plus 3. This is pretty quick because we only have a couple steps. So then we have our 2x squared divided by x, which is 2x. Multiply it back down, so we get 2x squared, and then we have minus 4x. Change the sign, we add straight down, we get 1. X plus 3, and then when we divide x and x, we get a 1, right? Now from there, it's not going to matter. We'll have a remainder. So watch me graph this. We have a y-intercept of 1, up 2 over 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 1, down 2 over 1. So now I have this oblique asymptote. Okay, so now from there we're going to find x-intercepts, y-intercepts. This one's actually pretty interesting. So x-intercepts is what makes the numerator 0. I'm not going to even find that right now because it's going to be either quadratic formula, right? If you can't factor, we've got to use quadratic formula. Nah. Y values, let's find the y-intercept. That's when x equals 0. So that would be negative 3 halves. You plug in 0. So look, over 0, down 1 and a little bit. Okay. Now, we can plug in more points. So notice on this side of the graph, I can plug in a 3. Everybody, if you wouldn't mind, quickly plug in a 3 for me. Then somebody else plug in, look on this in here, I'm going to plot at least another point. So plug in a 1. Then I'm going to plot on this side of the asymptote because we've got to fill in all of our x's. So someone else plug in negative 2. Pick one, plug it in for me so we can be quickly done here, but it's interesting what happens. It even kind of threw me off for a second last hour. What is 3 is 12? Okay. Okay. It is a, okay, minus 4.25, you said roughly? Okay, so watch me plot those points. I go over 3 up 12 units. Isn't that going to put me in this section? So over 3 up 12, that's like clear up here. Now look, we know it will never cross this asymptote, so it must be approaching it, and it will never cross a oblique asymptote. So it must be coming down, curving, and then going back like that. So it can't cross it. Does that make sense? Now in this section of the graph, we have a 0.1, negative 2, so that's right here. And negative 2, okay, so in this section of the graph, and then negative 2, and then it looks like negative 2.5. Negative 4.5, that's like right here, isn't it? So we can see what's happening. It will not cross the oblique, there it is following it. It's coming up, and then it's circling and following this oblique. Now, if you plot any more points over here, it'll always fall within this asymptote right here. So there's not anything up here. There's not anything in here. That's the end. No matter what point you plot, it'll fall within here or here. So you're done. Is everybody good? I mean, it makes sense. It shouldn't cross oblique, and it shouldn't cross vertical, so it would have to stay inside, right? Now, otherwise, like, and there are graphs, like it could have, if we would have graphed it, it could have been like this. And like this. You see how that's following the asymptote? So your points will tell you where to go. Your points will tell you where to go. Okay, now I do believe that you would be good to just start practicing. Sorry about that. Ready, go. Back page.